Well, this is a moment many of you have been waiting for a very long time. This is the last definition of an integral that you're going to see not only in this class, but in your entire undergraduate calculus career. So, big moment. Glad for you. Let's knock it out and wrap up this section. So, we're going to work with a vector field big F and an oriented surface S with unit normal vector n. And what am I saying? Well, when you've chosen your unit normal vector n, when you specify the formula for n, you have oriented S. And you need to do that at the beginning. And either way, either of the orientations you pick, that's fine, but you need to realize when you choose n, you are orienting S. And that may or may not matter depending on your context. So I also want to assume that the components of my vector field F are continuous on this surface. All right, so then the surface integral of a vector field F over our surface is defined as, well, we write it like this. We say surface integral over S of vector F, and then I'm going to dot with the vector, or with ds, where I'm thinking about S on the end here is actually a vector. You'll see it bolded in your book. And this is defined as the surface integral over S of F dot your normal vector n ds without a vector symbol on it. And I know we've been looking at all kinds of integrals. You've got integrals bouncing all around, but this is the last one, and we need to make sure that we get the notation clear here. And so there is some information wrapped up in this notation. Notice that here, for the first one, the one that I started with, I'm integrating a vector field, and I'm dotting with, well, a vector at the end, okay? And then this ds, this vector, I want you to think about it as n times ds. And the real change is when we had a D capital S before, that's what we put at the end of surface integrals of scalar functions. Let me squeeze that in pick. If we had if we had a surface integral of a scalar function, little f, I would have put a ds there, right? And, well, that's the same ds. What gives? Well, look, when you dot two vectors, what do you get? You get out a scalar. And so I'm going to get a scalar function here. And so the point is that surface integrals of vector fields can be translated to surface integrals of scalar functions in that way. That's the way that you do it. And so the symbology here, no vector S, just plain big S, versus this vector S is keeping track of that for us. And so this is called, by the way, this has a name, this is called the flux of F across S. I'm going to tell you how to think about this, how to visualize this in a few minutes. I wanted, though, to focus on a useful formula for these guys. So let's go ahead and call this star. And so how can we translate this into something practical that we can actually work with? So suppose with me that S, our surface S, is parametrized by R of U and V. Then we're going to change star a little bit. So certainly this is that, and that's what I've got here. Okay, so now we're here. And then I want to think about each of these pieces. I want to focus with you on this unit normal vector n and then this ds. I've already got it written out. N, because n, we said is just r partial u cross r partial v divided by length to make it a normal vector. So that's n. And then we always have d capital S is, I'm going to make this a little neater because it's kind of hard to read. This is just r partial u cross r partial v length and then dA. That's the idea. And so you cancel these two pieces. And also, by the way, I didn't write it here, but when you switch this thing, right, when you switch this to a double integral, I should put a d over here too. When you switch this to a double integral, you're actually plugging your parameterization into F. And so we end up with a double integral over d of f of r of u and v dot ru cross rv dA. And so the point is, at the end of the day, this is the formula you're going to use to compute surface integrals of vector fields. You're going to jump right here most of the time. Sometimes we'll actually realize, oh, look, we have an easy formula for our unit normal vector, and we can just use that and head off to the races. So I'll do examples of all that with you. So the key takeaway is this relationship. So when you have the surface integral of a vector field, right, this becomes a double integral over the region D, defining your U and your V, of f of, plug in the parameterization, f of r of u and v, dot with r partial u cross r partial v dA. That's the key takeaway that you need to have. And I'm going to add these formulas to the formula sheet that I already started. I had a bunch of formulas for line integrals, and I will add these different formulas for surface integrals. All right, so one last comment is I just want to make sure that you notice the strong similarity between surface integrals of vector fields and line integrals over vector fields. So look at the similarity with me. If I have a surface integral of a vector field, I write it f dot ds. If I have a line integral of a vector field, I write it f dot d vector r. In this case, for the surface integral, I have f of, plug in the parameterization, dot with the derivative, so to speak. Same with line integrals, f of, plug in a parameterization, dot with a derivative, so to speak. So I know this is challenging. We've got integrals flying around, but if you'll pay attention to the patterns here, that's what mathematics is after all. If you'll pay attention to the patterns here, then it really will help you know what to do. These problems actually aren't that different than what we've been doing, other than now we have parameterizations of two variables. So I'm going to break this video here, and then I'll do the next couple of videos over example.